Ben Franklin understood where the electrical energy was stored in a capacitor. His conclusion conflicts with how physics describes capacitors today. This video will describe that conflict and show you how to prove that Benjamin Franklin was right. This is the basic outline that we are going to follow. Now, why does it matter that we understand how a capacitor works? First of all, a capacitor is a very fundamental component in our electronics today. If we were to take the capacitors out of our phones, computers, cars, TVs, everything would stop working. And today, if we can better understand how to store electrical energy, it can help make improvements in our mobile electronic devices, our electric vehicles, and improve electrical storage on our power grid. Those are good practical examples, but when you better understand how a capacitor works, you can then apply it to nature and to physics, because these capacitor principles are fundamental to our electrophysical world. So let's take the periodic table and chop it into two pieces. For our discussion today, we only care about metals and nonmetals. And the words we will use for nonmetals are insulator or dielectric. So simply said in today's physics terms, metals are the wires that conduct the current, or inside those wires, the electron flow is the current. The insulator is the plastic coating around the wire, and it is used to help keep the wires from touching each other. And again, we're going to call that plastic insulator a dielectric. The first capacitor built is known as the Leiden Jar. Let's take a look at how the Leiden Jar is constructed. The Leiden Jar typically used glass as an insulator between the two tinfoil layers. So in this case, the glass insulator is the dielectric material for this form of capacitor. A piece of metal was then pierced through the lid of the jar to make contact with the tin foil that lined the inside of the jar. This is a picture of two Leiden Jar capacitors that were taken from the ship that saved passengers from the Titanic sinking. These capacitors were used in the radio system. The broken one on the right shows the inside construction of the jar, and typically it was filled with some type of water solution because you can see the corrosion on the copper wires. Now let's take a look at how electrical energy is stored in a capacitor. We have two conflicting viewpoints. So first, let's take a look at how Benjamin Franklin described where the electrical energy was stored in the Leiden Jar. This is Benjamin Franklin's book on electricity. It was printed in 1751. On page 24, you will find his answer. So let's read this sentence. Thus the whole force of the bottle and power of giving a shock is in the glass itself. So it is clear that his conclusion is that the dielectric material held the electrical energy that produced the shock. In this case, the dielectric is the glass. The next sentence describes what the metal surfaces do. Back then, the metals were considered non-electrics, which seems a bit backwards using today's standards. You could just use the word non-dielectrics here. Back to the Wikipedia page, let's note that Ben Franklin was the inventor of the Leiden Jar that could be taken apart into pieces, or it's now known as the Dissectible Leiden Jar. He also made the first parallel plate capacitors that could be pulled apart and inspected. So most likely these inventions helped him to conclude that the energy was stored in the dielectric. Now let's look at it from a physics point of view, which uses free electron theory to describe the energy storage of a capacitor. From a physics viewpoint, the energy of a capacitor is stored in the metal plates and not directly in the dielectric. We will use this FET simulation to help us understand the electron flow in this circuit. As we energize the wires by using a power source, such as this battery, notice that the two capacitor plates are accumulating charge. One is positive and one is negative. The idea is that the metal in the wires contain electrons that are free to move and flow from one plate to the other. This creates an electrical imbalance between the two plates. Since the electron is a negatively charged particle, the negative plate is filling up with electrons. This leaves the positive plate in a position where it is continually giving up electrons. Now we can add a dielectric material in between these plates if we like, and that changes the electrical capacity that can be stored. But if we remove the dielectric from this field, it should not have any charge on it, since the electric field is produced by the imbalance of this plate and this plate. So the real test of this free electron theory would be to remove the dielectric that's in this electric field, and then use that same dielectric and discharge it using two different metal plates. Next, I will show you this type of demonstration, and the setup looks very similar to this. For the power generation source, I use what's called a Wimshurst machine. For my capacitor, I'm going to use a plastic JIF jar, and then we will discharge the capacitor using a fluorescent light bulb. Before I start my experiment, I will give you some other examples of dissectible Leiden jar videos. The first video is by Professor Julius Sumner Miller. You can search by the title of the video and then move forward to the 10-minute mark. This is where the Leiden jar demonstration starts, and even though he doesn't explain how it works, he suggests that any student that can explain it should get an A. The next video is from MIT professor Walter Lewin. His demonstration starts at the 39:30 mark. So in this third video, Professor Lewin gives his explanation to what's going on. If you go to the 32-minute 45-second mark in the video, he will justify his conclusion using math. And in my demonstrations, I will use different jar configurations to eliminate the theory that he suggests. And here are two videos that show the same test, except they use parallel plate capacitors instead of the Leiden jar. Okay, let's describe the lab setup. We have a JIF peanut butter jar. One electrode from the Wimshurst machine is attached to this piece of metal. So this acts as my top plate. It pierces through the plastic lid, and a small 12-gauge wire is hooked to it on the inside. This wire is bent so that the end is just barely above the surface of this liquid. The liquid is distilled water with a little bit of canola oil and some food coloring. Finally, the bottom plate here is just a backing plate to an electrical box, which is then connected to the other electrode of the Wimshurst machine. Over here we have a fluorescent light bulb and two alligator clips attached to this light bulb, and this is used to discharge the capacitor. So this first demonstration is just going to show you how I utilize all this equipment. First, I want to make sure that the Wimshurst machine is generating a charge. Now I'm charging up the capacitor using the Wimshurst machine. And now I'll take off the electrodes and then discharge the energy that's stored in this capacitor. This is a screenshot of the capacitor discharging, and you can see the corona arc right there. The fluorescent light bulb lights up. There's light reflection off of the plastic jar, but if you look inside, you'll also see a discharge that comes off the liquid onto the copper wire. So the reason why I configure this jar with this dangling wire here is because I want to see the motion in the different dielectric solutions that I put into the jar, and I'll be able to see the reaction of the wire while I'm charging the jar. So for this next demonstration, I want to make sure that you realize I have two different plate sets. I'm going to charge up the jar using the plate set on the left, and then we'll take those off, push them to the side, and then utilize a completely different top and bottom plate to discharge it. Okay, this one's going to be in a darker environment so we can see the corona discharge throughout the experiment. Sorry for the annoying squeak on the Wimshurst machine. Okay, now we're going to remove the top and bottom plate so there'll be no metal. Switch the jar over to a completely different set of plates. All new metal, and then we're going to discharge it. And this should show that the energy of a capacitor is stored in the dielectric and not in the metal. This is a screenshot of the capacitor discharge that we just saw. You can better see the corona discharge that happens inside the bottle. There are also small corona streamers that you can see coming up around the bottom of the container, and then the obvious discharge and the lighting of the lamp. This experiment is similar to the last one we did, but when we're charging this capacitor, what I'm trying to do is eliminate more of the metal. So you can see the bottom plate is now styrofoam, and the electrode is just placed underneath the plastic jar. When we go to discharge, it will add back in a metal bottom plate, but we won't use the metal top plate. Okay, so instead of putting back another top plate, what we're going to do is just put a wire inside of the jar and put the wire into the liquid and then discharge it on the new bottom plate. So again, this shows that we've completely changed out all of the metal, but yet still get an electrical discharge from the plastic. And over here you can barely see the corona discharge from the copper wire that's down inside of the liquid. Okay, we're going to use a new jar for this test. And the idea is that we're going to try to insulate this jar as much as possible while we're charging it. This will be a direct challenge to MIT professor Walter Lewin's explanation on how the dissectible Leiden jar works. We need to minimize the amount of metal that is near this capacitor. This is so we can eliminate the idea of the metal spraying charge onto the capacitor. We're going to use an insulated wire, and the copper end that is inside the jar will be submerged in distilled water. The insulated wire will be going through this small hole at the top of the JIF jar. If you're unfamiliar with how good of an insulator distilled water is, I recommend that you watch this video from the plasma channel. You can get a great understanding of how distilled water is a very good insulator and not a conductor of electricity. So we're keeping the room really dark so we can see if there's any corona discharge occurring. The only metal that I have on the bottom of this jar is the actual alligator clip from the Wimshurst machine. Now we're going to add in metal in order to get this thing to discharge fast. So we're putting on one of the old tops, and we're going to replace the bottom styrofoam with one of the other metal plates. Again, that's so we can see the discharge. So that eliminates the idea of metal spraying charge onto the jar. Now we see that dielectrics can store energy. Ben Franklin's idea that the energy was stored in the glass is correct. So for me, that does say that there's something wrong with the physics viewpoint. The free electron theory does not properly explain how energy is stored in a capacitor. And hopefully these demonstrations can help you figure out how to find that answer on your own. I bought this from eBay. It's a 9-inch Wimshurst machine and shipped from China. It was like 50 bucks. If you're going to get into this, stay with the small stuff, small capacitors, because you will get shocked. And if you have small capacitors, it's not going to hurt as bad. Another device I have is a Thomas Kim electroscope. So I built this one based upon his design, and what's great is it shows the polarity of these dielectrics after you charge them. You can see the positive side on the bottom and the negative side on top. So the idea is to keep this as simple as possible and not require anything too fancy to be able to do these types of tests. This experiment was using canola oil as the liquid dielectric, and you'll see when it discharges it doesn't snap. In this one you can see the dielectric start climbing up the walls of the jar. This is a mixture of canola oil and distilled water. So to finish up the video, I can suggest the reading that I've been doing. We have to go back to 1861 with Clerk Maxwell's theory on dielectric displacement, and then we can continue forward through all the other great electricians. Eric Dollard is a contemporary electrician, and he is currently publishing books on his research. Okay, that wraps up the video. Thanks for watching, and until next time.